Take a breath right now, through your nose. Now take another one through your mouth. Same lungs, same air, same oxygen concentration, same tidal volume moving in and out of the same respiratory system. By every measure that seems to matter, those two breaths are identical, and yet they are not. The brain that receives the signal from those two breaths is in a measurably different chemical state depending on which route the air took to get there. Not slightly different, fundamentally different. Different enough that researchers can measure the difference in blood flow, in neural oscillation patterns, in autonomic nervous system tone, and in the concentration of a specific molecule in the air reaching your lungs that your body depends on for functions ranging from vascular regulation to immune defense to cognitive performance. That molecule is nitric oxide, and your sinuses are the largest nitric oxide factory in your body. Every breath you take through your nose carries a dose of nitric oxide produced in your paranasal sinuses directly into your airways and lungs. Every breath you take through your mouth bypasses that factory entirely. The lungs receive no nitric oxide. The blood vessels in the lungs receive no nitric oxide signal. The brain receives a subtly but meaningfully different chemical message. And over the course of a lifetime of breathing, the route the air takes turns out to matter enormously. To understand why, you need to know what nitric oxide actually does. In 1998, the Nobel Prize in Physiology or Medicine was awarded to Robert Furchtgott, Louis Ignarro, and Farid Murad for their discovery that nitric oxide is a signaling molecule in the cardiovascular system. Before their work, nitric oxide was primarily known as an air pollutant, a component of smog and combustion exhaust. The idea that the body produces it deliberately in precise quantities for specific physiological purposes was not just surprising, it was paradigm shifting. Nitric oxide turned out to be one of the most versatile signaling molecules in mammalian biology. It regulates vascular tone, causing smooth muscle and blood vessel walls to relax and the vessels to dilate. It modulates the immune response, being produced by immune cells as a weapon against pathogens. It functions as a neurotransmitter in the nervous system, involved in learning, memory consolidation, and the regulation of synaptic plasticity. And it is produced in enormous quantities by the epithelial cells lining your paranasal sinuses, the air-filled cavities in the bones of your face that connect to your nasal passages. When you breathe through your nose, the air passes through or beside these sinuses, picking up the nitric oxide they produce and carrying it down into your trachea, bronchi, and ultimately, your alveoli. In the lungs, nitric oxide from nasal breathing causes pulmonary vasodilation, relaxing the smooth muscle in the walls of the pulmonary blood vessels and increasing blood flow through the lung tissue. This improves the ventilation perfusion matching of the lungs, which is the efficiency with which the areas of the lung receiving air are also receiving blood flow. Better ventilation perfusion matching means more efficient oxygen transfer from the air into the bloodstream. The same breath, carrying the same amount of oxygen, delivers more of that oxygen to your blood when it enters through your nose than when it enters through your mouth, because the nitric oxide from nasal breathing optimizes the pulmonary circulation to receive it. Studies measuring arterial oxygen saturation have found small but consistent differences between nasal and mouth breathers, with nasal breathing producing slightly higher oxygen saturation for equivalent ventilation. In normal, healthy individuals at rest, this difference may seem trivial, but during exercise, during sleep, during any situation where oxygen delivery is at a premium, the difference in pulmonary efficiency between nasal and mouth breathing can become clinically meaningful. This is one of the reasons why elite endurance athletes are increasingly training with nasal breathing protocols even during high-intensity exercise, a practice that initially seems counterintuitive given the greater airflow resistance of nasal breathing compared to mouth breathing, but that appears to produce adaptations in respiratory efficiency and CO2 tolerance that improve performance over time. But the story of nitric oxide and nasal breathing goes well beyond pulmonary efficiency. Nitric oxide, produced in the sinuses and delivered by nasal breathing, also reaches the cerebral circulation, where it acts as a vasodilator on the blood vessels supplying the brain. Nasal breathing is associated with measurably greater cerebral blood flow than mouth breathing at equivalent ventilation rates. The brain receives more blood, more oxygen, and more glucose per unit time during nasal breathing than during mouth breathing, not because you are breathing more, but because the nitric oxide signal is optimizing the vascular response to the respiratory cycle. This effect on cerebral perfusion is not a small or marginal phenomenon. It is measurable with functional imaging techniques, and it has behavioral correlates in cognitive performance studies showing improved attention, working memory, and reaction time associated with nasal breathing conditions. There is a second mechanism connecting nasal breathing to brain chemistry that is entirely independent of nitric oxide, and it involves one of the most ancient and direct connections between the external environment and the central nervous system. The olfactory nerve, the first cranial nerve, is the only sensory pathway in the human body where neurons project directly from the external environment into the brain without passing through the thalamus, the relay station that processes virtually all other sensory information before it reaches the cortex. Olfactory receptor neurons in the nasal epithelium send their axons directly through the cribriform plate of the ethmoid bone into the olfactory bulb, which projects directly to the piriform cortex, the amygdala, and the hippocampus. This direct line from the nose to the limbic system, to the brain regions most involved in memory, emotion, and fear processing, is the anatomical basis for the extraordinary power of smell to evoke memory and emotional states. But what is less appreciated is that nasal airflow itself, independent of any olfactory stimulus, influences the electrical activity of these limbic structures. Airflow through the nasal passages generates rhythmic signals in the olfactory epithelium that synchronize with the breathing cycle. These rhythmic inputs to the olfactory bulb create oscillatory activity that propagates into the hippocampus and prefrontal cortex, synchronizing neural oscillations in these regions with the respiratory rhythm. This respiratory neural coupling, the synchronization of brain rhythms with nasal airflow, appears to play a functional role in memory encoding and emotional regulation. Studies using intracranial recordings in humans have found that memory encoding is more effective during the inhalation phase of nasal breathing than during exhalation, and that this effect is significantly reduced or absent during mouth breathing, which does not generate the same rhythmic olfactory input to the limbic system. The breath you take through your nose is not just delivering air to your lungs. It is sending a rhythmic electrical signal directly to your hippocampus, and that signal is part of how your brain consolidates what you experience into memory. Now consider what happens at night. Chronic mouth breathing during sleep, which affects a significant portion of the adult population due to nasal congestion, structural nasal abnormalities, or habitual patterns, has consequences that extend far beyond the absence of nasal nitric oxide. Mouth breathing during sleep is associated with snoring and with an elevated risk of obstructive sleep apnea, because the oral airway is less structurally stable than the nasal airway during sleep and more prone to collapse. Sleep apnea, as we have discussed in other contexts, severely disrupts sleep architecture, impairs glymphatic function, and is associated with accelerated cognitive decline. But even absent frank sleep apnea, chronic mouth breathing during sleep disrupts the CO2 balance of the blood in ways that affect sleep quality. Nasal breathing during sleep is associated with higher end-tidal CO2 levels, which is actually beneficial because CO2 is the primary driver of the vasodilatory response in the cerebral circulation. Higher CO2 during sleep means better cerebral blood flow, deeper sleep stages, and more efficient glymphatic clearance. Mouth breathing, by increasing ventilation and lowering CO2, reduces the vasodilatory drive to the brain during sleep and contributes to lighter, more fragmented sleep architecture. The autonomic nervous system is the third major channel through which nasal breathing changes brain chemistry. The vagus nerve, the 10th cranial nerve, and the primary conduit of the parasympathetic nervous system, carries signals between the brain and virtually every major organ in the thorax and abdomen. Vagal tone, the baseline level of parasympathetic activity transmitted through the vagus nerve, is a marker of cardiovascular health, stress resilience, and emotional regulation capacity. High vagal tone is associated with greater heart rate variability, lower resting heart rate, lower inflammatory markers, and better outcomes across a wide range of cardiovascular and psychiatric conditions. Low vagal tone is associated with anxiety, depression, hypertension, and chronic inflammation. Nasal breathing, particularly slow nasal breathing at rates around 5 to 6 breaths per minute, is one of the most powerful acute and chronic enhancers of vagal tone. The mechanism involves the stretch receptors in the lungs and the baroreceptors in the thoracic vessels, which send afferent signals to the brainstem via the vagus nerve. Slow, deep nasal breathing maximizes the activation of these receptors and the parasympathetic reflex arc they trigger, reducing heart rate, lowering blood pressure, and increasing heart rate variability with each breath. The nasal resistance itself, the slightly greater resistance to airflow through the nose compared to the mouth, may contribute to this effect by slowing the respiratory rate and increasing the depth of each breath, both of which enhance vagal activation. Mouth breathing, with its lower airflow resistance, tends to produce faster, shallower breathing patterns that reduce the activation of the parasympathetic reflexes and maintain a higher sympathetic tone. This is why slow nasal breathing is the foundation of virtually every evidence-based breathwork protocol for anxiety and stress reduction. Not because of any mystical property of breathing, but because of the direct, measurable effect of slow nasal airflow on vagal tone, heart rate variability, and the balance between the sympathetic and parasympathetic branches of the autonomic nervous system. Every slow nasal breath is a dose of parasympathetic activation, delivered through the oldest and most direct pathway connecting the respiratory system to the brain. There is one more dimension of nasal breathing that deserves attention because it connects the chemistry of breathing to the biology of infection and immune defense. The nitric oxide produced by the paranasal sinuses is not only a vasodilator and neurosignaling molecule, it is also a potent antimicrobial agent. Nitric oxide has direct virucidal and bactericidal activity, disrupting the replication machinery of viruses and bacteria that enter the respiratory tract. The nasal passages, by continuously bathing the inspired air in nitric oxide before it reaches the lower respiratory tract, provide a first line of chemical defense against inhaled pathogens. Studies during the COVID-19 pandemic found that nasal high-flow nitric oxide inhalation had antiviral effects against SARS-CoV-2 in vitro, consistent with the known antimicrobial properties of the molecule. Mouth breathers, who bypass this chemical defense layer entirely, deliver unfiltered air directly to the lower respiratory tract without the nitric oxide pre-treatment that nasal breathing provides. This is one of the biological reasons why nasal breathing has been associated with lower rates of respiratory infection in epidemiological studies, and why the first advice given by respiratory physicians during epidemic seasons is often simply to breathe through your nose. Step back now and look at the full picture. Your nose is not a filter. It is a neuropharmacological interface between the external environment and your nervous system. Every nasal breath delivers nitric oxide that dilates your pulmonary and cerebral vasculature, improves oxygen delivery, and synchronizes your brain chemistry with the respiratory rhythm. Every nasal breath sends rhythmic signals through the olfactory nerve directly to your hippocampus and limbic system, coupling your brain's electrical activity to the act of breathing. Every slow nasal breath activates the vagus nerve and shifts your autonomic nervous system toward the parasympathetic state that is associated with calm, cognitive clarity, and cardiovascular health. And every nasal breath bathes the inspired air in a molecule that has Nobel Prize-winning biology and direct antimicrobial activity against the pathogens you inhale every day. And mouth breathing bypasses all of it. The same air, the same lungs, the same oxygen, but none of the chemistry, none of the nitric oxide, none of the olfactory synchronization, none of the vagal activation from nasal resistance, none of the antimicrobial pretreatment. Just air arriving at the lungs through a route that evolution did not design for primary respiratory use, without the neuropharmacological payload that the nasal route has been delivering for the entire evolutionary history of the human respiratory system. The nose is not the backup airway, it is the primary one. And the mouth is the emergency backup that most modern humans have made their default. The consequences of that switch, lived out in the chemistry of millions of breaths per year, in the baseline tone of the autonomic nervous system, in the nightly architecture of sleep, in the chronic levels of nitric oxide reaching the brain, accumulate quietly over decades. And they show up as the anxiety that will not quiet, the sleep that will not deepen, the attention that will not focus, the blood pressure that will not come down, the infections that come a little more often than they should. The solution is as simple as the mechanism is complex. Breathe through your nose. Not as a relaxation technique, not as a wellness practice, as the primary operating mode of the respiratory system that evolution built for you, the one with the nitric oxide factory, the one with the direct line to the hippocampus, the one with the vagal activation, the one with the antimicrobial chemistry, the one your body has been waiting for you to use. That is applied biology. In every breath you take through your nose, starting right now. There is one more layer to this story that brings everything together in a way that most people never consider. It involves the nasal cycle, a phenomenon so counterintuitive that most people refuse to believe it when they first hear it. And yet, it has been documented in the scientific literature for over a century, and its functional significance is only now becoming clear. Right now, at this moment, you are breathing predominantly through one nostril, not both equally. 1. The nasal passages contain erectile tissue, similar in structure to the erectile tissue elsewhere in the body, that swells and shrinks on a controlled cycle, regulated by the autonomic nervous system. Every 90 minutes to 4 hours, the dominant nostril switches. The left nostril becomes more patent, while the right constricts. Then the cycle reverses. This alternating nasal cycle is universal in healthy humans, and in most people it passes entirely unnoticed. You simply do not register that your airflow is preferentially through one side. But here is why it matters. The two sides of your nasal passages connect through slightly different anatomical routes to slightly different regions of the brain. The right nostril preferentially activates the left hemisphere, associated with analytical thinking, language processing, and sympathetic nervous system tone. The left nostril preferentially activates the right hemisphere, associated with spatial reasoning, creative thinking, and parasympathetic nervous system tone. This hemispheric asymmetry of nasal influence, documented in studies measuring EEG activity and cognitive performance during forced unilateral breathing, means that the nasal cycle is not just a quirk of nasal anatomy. It is a rhythmic driver of alternating hemispheric dominance, cycling the brain between states of greater analytical focus and greater creative parasympathetic tone on a roughly 90-minute schedule that maps almost perfectly onto the ultradian rhythm, the 90-minute cycle of alertness and slight cognitive relaxation that researchers have documented in human waking performance throughout the day. The nasal cycle and the ultradian rhythm may be the same biological oscillation, expressed simultaneously in the nose and in the brain. The nose is not passively following the brain's rhythm. It may be actively driving it. Every time the nasal cycle shifts, the autonomic balance and the hemispheric dominance shift with it, creating a biological rhythm of cognitive state that you have been living inside your entire life without knowing it existed. This is the full picture of what nasal breathing does to your brain chemistry. It is not one mechanism. It is a network of mechanisms, all operating simultaneously, all dependent on the same simple physical act of routing your breath through the nasal passages rather than the oral cavity. Nitric oxide production and delivery, olfactory synchronization of hippocampal and prefrontal oscillations, vagal activation through nasal resistance and slow respiratory rhythm, antimicrobial defense of the lower respiratory tract, and the rhythmic, alternating hemispheric activation of the nasal cycle, cycling your brain through states of focus and restoration on a schedule that the body set for itself long before you were conscious of it. Every one of these mechanisms is dependent on nasal breathing. Every one of them is bypassed by mouth breathing. And every one of them has been operating, or failing to operate, in your body every day of your life, shaping your cognitive clarity, your emotional resilience, your sleep quality, your cardiovascular tone, and your resistance to infection based on the simple, invisible, unconscious choice of which opening you use to bring air into your body. You have approximately 23,000 breaths today. Each one is a choice, even if you never consciously make it. Each nasal breath is a dose of nitric oxide, a pulse of olfactory synchronization to your hippocampus, an activation of your vagus nerve, a small contribution to the parasympathetic balance that determines your baseline state of being. And each mouth breath is none of those things. It is just air, the same air, but arriving without the chemistry that your nervous system was designed to receive with it. The nose is a neuropharmacological organ. It produces molecules that regulate your brain. It sends signals directly to the structures that govern your memory and your emotions. It drives the rhythms that cycle your cognitive states through the day. It is, in the most literal biological sense, part of your brain's operating system. And it has been sitting in the center of your face your entire life, doing this work, waiting to be understood. Now you understand it. Applied biology in every breath you take through your nose, starting with the next one. Let me give you the final piece of this picture, because it connects the neuropharmacology of nasal breathing to something that will make you permanently aware of your own breath in a way you were not before. It involves carbon dioxide, and it involves one of the most widespread and least understood breathing dysfunctions in modern life. Most people think of carbon dioxide as simply the waste product of cellular respiration, the thing you breathe out, the byproduct your body is trying to get rid of. And that is partly true. But CO2 is also a signaling molecule of extraordinary importance in the regulation of the respiratory and cardiovascular systems. CO2 in the blood is the primary driver of the respiratory drive. It is CO2, not oxygen, that tells your brainstem to make you breathe. When CO2 rises, you breathe. When CO2 falls, the drive to breathe diminishes. And CO2 is a powerful vasodilator, particularly in the cerebral circulation. More CO2 means more blood flow to the brain. Less CO2 means less. Modern humans, largely because of chronic mouth breathing, chronic stress, and sedentary lifestyles, tend to overbreathe. Not dramatically, not obviously, but subtly and chronically. They breathe at rates that are slightly higher than physiological requirements, keeping their CO2 slightly lower than optimal. This chronic mild hypocapnia, low CO2 from overbreathing, has consequences. It reduces cerebral blood flow. It increases the excitability of the nervous system, contributing to anxiety and hypervigilance. It disrupts the delivery of oxygen from hemoglobin to tissues through a mechanism called the Biot effect, where lower CO2 causes hemoglobin to hold onto oxygen more tightly rather than releasing it to the cells that need it. The blood carries plenty of oxygen, but it delivers less of it to the tissues because the CO2 that signals hemoglobin to release its oxygen is chronically suppressed. Nasal breathing, with its greater airflow resistance compared to mouth breathing, naturally slows the respiratory rate. A slower respiratory rate means CO2 has more time to accumulate between breaths, maintaining higher end tidal CO2 levels and keeping the cerebral vasculature appropriately dilated. Nasal breathing is a structural corrective for the overbreathing tendency that mouth breathing enables. The resistance is not a bug, it is a feature. It is the body's built-in governor on the respiratory rate, keeping CO2 in the range where oxygen delivery is optimized, cerebral blood flow is maintained, and the nervous system is not chronically driven toward hyperexcitability by the low CO2 state that rapid mouth breathing produces. This is why the practice of nasal breathing during exercise, despite the initial discomfort of breathing through a higher resistance airway while demanding more oxygen, produces adaptations over weeks and months that many practitioners describe as a kind of respiratory recalibration. The CO2 tolerance increases. The overbreathing drive diminishes. The respiratory rate at any given workload decreases. The nervous system becomes less reactive to CO2 fluctuations. And the brain, maintaining higher average CO2 and therefore higher cerebral blood flow, operates with greater clarity and lower baseline anxiety. Not because anything exotic happened, because the respiratory system returned to operating within the parameters it was designed for. The nose is the regulator, the mouth is the override, and modern life, with its chronic nasal congestion from allergens and pollution, its structural changes from soft diets that reduce jaw development and nasal airway volume, its stress-driven respiratory patterns that favor rapid chest breathing through the mouth, has made the override the default for a substantial fraction of the population. The consequences are not dramatic. They are subtle and chronic. They live in the background of daily experience as the vague anxiety that will not fully resolve, the sleep that will not fully restore, the focus that requires more effort than it should, the blood pressure that sits a little higher than ideal, the respiratory infections that come a little more often, the cognitive performance that never quite reaches its potential. All of it connected through the mechanisms we have covered today, to the chemistry of how you breathe, to whether the nitric oxide from your sinuses reaches your lungs and your brain, to whether the olfactory nerve sends its rhythmic signal to your hippocampus with each inhalation, to whether the nasal resistance slows your breathing enough to keep your CO2 in the range where your brain is optimally perfused and your hemoglobin releases its oxygen. To weather the nasal cycle drives its alternating hemispheric rhythm through your waking day. 23,000 breaths today, each one a neuropharmacological event if you take it through your nose, each one just air if you take it through your mouth. The difference is not in the lungs, it is in the chemistry, and the chemistry is in the nose, the organ that was always right in the center of your face, doing this work, waiting for you to understand what it was for. Now you do. Applied biology, in the most ordinary and most overlooked act of being alive. Breathing. Done right, through the right opening, with all the chemistry intact. Starting now. And here is the practical reality that makes all of this immediately actionable in a way that most biology is not. Unlike sleep quality, which requires changes to your environment, your schedule, and your habits over weeks. Unlike diet, which requires planning, preparation, and sustained behavioral change. Unlike exercise, which requires time, equipment, and physical effort. Nasal breathing requires nothing except awareness. You do not need to buy anything. You do not need to schedule anything. You do not need to learn anything new. You need to close your mouth and breathe through your nose. That is the entire intervention. Available to you right now, in this moment, for every one of the 23,000 breaths you will take today. The nitric oxide factory in your sinuses is already running. It has been running your entire life. The olfactory pathway to your hippocampus is already wired. The vagal activation circuit is already connected. The nasal cycle is already operating. All of these mechanisms are in place, fully functional, waiting to deliver their chemistry to your brain and your cardiovascular system. They are just not being used when the air bypasses the nasal passages entirely. Close the bypass. Use the system. That is it. Of course, for many people, nasal breathing is not straightforward. Chronic nasal congestion from allergies, from structural deviated septum, from the gradual narrowing of nasal airway volume that has occurred across the population over generations as dietary softness reduced the mechanical forces that develop full jaw and nasal passage dimensions during childhood. These are real barriers that deserve real medical attention. If you cannot breathe comfortably through your nose, that is a treatable condition, not a permanent limitation. Addressing nasal obstruction, whether through allergy management, nasal irrigation, or structural intervention, is one of the highest leverage health investments available because it unlocks the entire cascade of nasal breathing benefits that we have covered today, not just during exercise or meditation or deliberate breath work, but for all 23,000 breaths of every ordinary day. The nose was always the primary airway. The science of why has been sitting in the literature for decades, scattered across cardiology journals and neuroscience papers and respiratory physiology textbooks, waiting to be assembled into a coherent picture. That picture is now clear. The nose is a nitric oxide delivery system, an olfactory brain synchronizer, a vagal tone regulator, a CO2 governor, and a hemispheric rhythm driver. It is, in every meaningful biological sense, part of the brain's interface with the world. And it delivers its payload with every single breath you take through it. Applied biology, 23,000 times a day.